Hey folks, Mr. Bauer here. In this tutorial I have three things I want to show you. So what is a derivative? What are the important derivatives we're going to be using in the study of motion? And how do you actually take a derivative? So, what's a derivative? Well, a derivative is a formula for the instantaneous rate of change of one variable compared to another. Let me make that a little more concrete. You're probably familiar with average velocity, which is delta x over delta t. How far something goes in a certain amount of time. You divide them, you get a ratio. Classic example of this is if you're driving your car and there's a speed trap on the road. So a speed trap, police are going to draw two lines. And then here you come along. You hit the first line. The cop starts some sort of a stopwatch device. You hit the second line, and the cop stops the stopwatch device. So what information does the cop have? Well, he knows how far apart the two lines, so he's got delta x. And from the stopwatch, he's got delta t. So we can get your average velocity and maybe see whether or not you deserve a speeding ticket. Now the problem with that for him is, let's look at another situation. Let's say you're moving along, you hit that first line, and you realize that it's a speed trap. So you hit the brakes hard, so hard in fact that you come to a complete stop before you get to the second line. And then you just wait there, maybe 5 seconds or so. And then you start up again. And then the cop stops his watch. Well, he still has your average velocity, but it's nowhere near the same number as, let's say, your instantaneous velocity at the very beginning. Maybe you were going 15 miles an hour over the speed limit here. But then since you came to a complete stop right there, the average really doesn't reflect this instantaneous value right here. So what can the cop do? What can the cop do to get a better and more accurate picture of your instantaneous velocity? Well, one idea that you might imagine is you put the lines a lot closer together. So maybe they're only that far apart. Then you have less room for slowing down or speeding up or whatever, and the average velocity that he comes up with is a lot closer to your instantaneous velocity. So what he's really trying to do here is to take the delta x and he's trying to shrink it as close to 0 as he possibly can. He wants to make the distance between these two lines really, really small. And at the same time, what that means is it's making the delta t as close to 0 as possible. Now, as long as it's not exactly equal to 0, there's still a little room for moving around here. It's still an average velocity. It's only if the delta t is equal to 0 that you really have an instantaneous velocity. But there's a problem. Look at this equation. If delta t equals 0, you're dividing by 0. And so mathematically, you get a nonsense answer. Well, that's the problem that derivatives solve. In a derivative, we say that delta t becomes infinitely small. Basically, it's equal to 0. And because that's a very special situation, we don't call it delta t anymore. We call it dt. So you're going to see that notation. A delta becomes a d when the interval becomes infinitely small. And so instantaneous velocity is labeled as dx dt. And that's a derivative. So let's see how to do that. Oh, yeah, here are the important derivatives in the study of motion. Well, we just mentioned instantaneous velocity is dx dt. It's how quickly x is changing as time changes in an infinitely small amount of time. The other important derivative in the study of motion is acceleration, instantaneous acceleration, dv dt. It's how quickly velocity is changing in a certain amount of time. So in the future, if you have to find instantaneous velocity, you're going to take the derivative of a position function. If you have to find instantaneous acceleration, you're going to take the derivative of a velocity function.